start off by doing a little bit of a description of what drives turbulence in the ocean. Caique did a great example of some of these processes. I'm going to kind of take a step back and talk a little bit more about sort of what those mean, kind of see it a little bit in math, a little bit maybe, but we'll walk through it. And then Caique will do a little bit of a discussion on sub-mesoscale processes, which he studies. So everyone yesterday did a great job of talking about turbulence in the ocean at different scales. So this is some pretty pictures. You saw a lot of things. Room is haunted. So some pretty pictures yesterday as well. These are some examples. You've got mesoscale eddies. You've got some Kelvin health hole instabilities, which we'll talk about. It's a bit of a teaser. And Charlotte, in her next lecture, will talk about how these different scales interact. And in this one, what we're going to focus on is what drives turbulence. So what's the process that's creating these kind of turbulent structures. So to kind of start simple, let's start with a water column of two different densities. So this is colored them here, yellow and blue, and then this is kind of a plot of what that looks like as a density profile. So when you have a mixing event, what happens is that you've got these two fluids kind of diffusing and mixing together, which is something we talked about and we just kind of reviewed this idea. So you still got a little bit of diffusion happening, kind of gradients at the edges of these two layers. Then you have this sort of homogenized fluid in the middle. And that's kind of, you were to go out in the ocean, obviously this is a very simple example, but this is kind of what we're looking for, is this sort of homogenizing of different layers of the ocean. And that's driven by instabilities. And that's kind of going to be the focus of our talk. I'll talk about some instabilities that are sort of largely driving vertical mixing. And Caique will talk about what happens when you sort of take 2D space into account and talk about this, the sub-mesoscale instabilities that drive mixing. So first, a kind of simple review of what it means to be in a sort of stable equilibrium or unstable equilibrium. Kind of simple example is thinking of a ball in different situations. So let's start with the first one there. So say you have a ball in a sort of overturned bowl, or in a bowl, not an overturned bowl, just in a bowl. Now, where is the PMC? Now, we were to displace this ball a little bit. This is kind of shifted a little bit in one direction. It's just going to go back to equilibrium. It's kind of what you'd expect. Sort of gravity brings it back to equilibrium. And this is known as a linearly stable kind of system. Now, if you have a neutrally stable system, any kind of displacement of the ball, it's just kind of in this flat plane, it's just gonna stay at equilibrium. It's just not gonna change. So that's a kind of example of a neutrally stable equilibrium. And then if you have a ball on a sort of overturned bowl, so kind of in this scenario here, any kind of small shift away from this kind of really precarious position it's on is going to cause it to just fall off the bowl. And so that's an example of a linearly unstable situation. So now you might be wondering, okay, well, we're using these words linearly. What's the nonlinear case? So in the nonlinear case, which is the case we see a lot in nature, the ball could be in kind of a stable equilibrium for small displacements. So that's if it gets pushed a little bit, it's going to kind of go back to its kind of equilibrium position. Now, if it's pushed a lot, so kind of entering this sort of unstable scenario, now it's going to become unstable, and it's just going to fall off this interesting looking ball. So that's kind of very general description of what these kind of different equilibrium positions look like and what might happen if you kind of displace this ball a little bit. So let's kind of think of this in terms of a fluid now. And actually, before I jump into that, any questions about kind of this simple model? So now, instead of kind of thinking of a fluid with two different colors of density, let's just kind of call them rho 1 and rho 2. So when you have a kind of stable equilibrium, if you just kind of shift this two-layer model a little bit, you're going to create disturbances that are kind of basically internal waves, which is kind of what Caique talked about. And it's just going to keep oscillating. It's not going to kind of change the overall kind of two-layer system that we have. And that's an example of a dynamically stable function. Now let's kind of think about how instabilities develop, right? We're thinking about turbulence. How do we get turbulence? So to think about that, we're going to add shear into this fluid. And I'm going to write this out a little, expand this diagram a little bit just to kind of help explain it. So kind of starting off with that two-layer model. So you've got fluid of rho 1, fluid of rho 2. And if you add shear to that, so that's something that's higher at the top and lower at the bottom. So what that kind of means in terms of the velocity field that you see, so let's just do the top layer, is you have a background flow, which is U1, and you add in little perturbation. So that's kind of that example, going back to that example of like a ball being displaced a little bit. So you add a little bit of the perturbation. This is what's happening along the x-axis. We're going to assume nothing's happening along the y-axis. And also assume that there's a small perturbation vertically as well. And when you have the same thing, you have a sort of similar situation in the lower layer of water as well. I'm not going to do the math for this. I'm happy to talk through it. I have gone through the proof for this. People are interested. But what happens when you have this sort of perturbation in the x-axis and the z-axis, as you see here, you can create a shift of the interface. So that's this described by this amplitude. And if you assume oscillatory solutions, you kind of get a general form of what that amplitude looks like. And note that when you solve this equation, we're assuming it's inviscid. So there's no viscous processes happening. And you're also linearizing this equation. So there's no non-linear processes. It is all a linear solution. And when we do that, let's kind of step back and kind of see what different values of taking like a wave number or frequency of this solution looks like, just to kind of build some intuition for what it would look like to have an instability case. And so in this scenario, K is going to be always real, but we assume that our frequency can take on both real and imaginary values. We'll kind of see what that means in the next slide. So let's just say we have K and omega, just real values. So when we do that, this is an example of that. It's just kind of an oscillatory solution. So what you can see is that if you have a real K and a real omega, you just get an oscillatory solution. Now let's look at a case where omega also has an imaginary number added into it. So if you do that math out, so if you take the exponential of that number, what you get is the oscillatory solution, as you see here, as well as an additional kind of exponential decay equation. So that is a scenario where you have a negative omega, and that is also imaginary. Now, if you have a positive omega, you get a scenario where when you expand that exponential, you get a situation where there's an exponential growth. And so, as you can imagine, probably, this is a scenario where you have a perturbation, which is kind of what I showed you initially. It's just kind of oscillating. It's not really changing the original kind of density structure. Here you have a scenario where you have a perturbation and that has sort of slowly decayed over time. And so kind of back to its kind of equilibrium position. But this is our sort of problem situation, right? We have a solution that's growing in time. So it's becoming more, the perturbation is growing. And as it grows, it has the potential to kind of develop nonlinear instabilities. And so that's sort of the scenario that drives. So if you kind of solve this, apply boundary conditions, so you kind of look at what's happening at the interface, you will get this dispersion relation. And Caique talked about this a little bit. It's kind of a relationship between the frequency and wave number of a wave that's kind of described by this situation, this kind of assumptions and boundary conditions we just discussed. So what I just showed you, just by kind of looking at solutions, possible solutions, is that an imaginary wave number and a positive wave number gives you conditions where you can have instabilities grow. So now, looking at this equation, what would be a situation where you would get an imaginary number? And feel free to take a few minutes to think about that one.
Yeah. What's under the square root? It's negative.
Mm-hmm. Yeah, exactly. Mm-hmm. Yeah. So, like Camilla said, what's under your square root of this equation is negative. You're going to get an imaginary number. And note that in the solution, you have two roots, right? So you have a case where you have a solution that's exponentially growing, and you have a case where you have a solution that's exponentially decaying. So it's really the exponentially growing solution that drives the instability. So you could probably sit and think about this a little bit, but I will do the math for you. And these are all slides that are available if you want to kind of go back and review this a little bit. But the scenario where you would get a negative number is if this value here is higher than this. Does everyone kind of see that? Okay. And so when you do the math out, and it's just a bit of algebra, you'll see that this condition here tells you a couple of things, right? Here you can see that if your velocity difference is large relative to your density difference, that is potential for an instability to grow. And the other scenario is if you have a very large wave number. And this is just kind of building intuition for now thinking of sort of the case where we'll have a continuous gradient. So I want to make sure everyone kind of understands this simple two-layer model first. So I'll stop here for questions if anyone has any. Okay. Yeah, before we move on to the continuous gradient, so even in this kind of simple two-layer model, you'll see with a perturbation, over time, you'll see these kind of billows forming. And these are called Kelvin-Helmholtz splits. So if we go solve this equation, plug in some values, this is kind of the evolution of an instability that you will see. Now let's kind of think.
Sorry.
Yes.
Can we go? I had the question was forming, and it's
Yes.
early.
Yeah. Sorry.
If you go back to the dispersion relationship slide, so this is different from the dispersion relationship we had seen yesterday.
Yeah. So what Caique showed was like it was including continuous gradient. This is a scenario where we're just kind of thinking of it's a two-layer model. So Caique's dispersion relation that he showed is what applies for internal waves in the ocean. So it's accounting for all of the forcing that affects an internal wave.
Okay. So yeah. Okay. So yeah, we just removed those other aspects of that. Okay.
Yeah. Yeah. This is just thinking about like the effect of the shear as well as just kind of gravity on the fluid.
Okay. Thank you.
Any other questions? Yeah.
It's a logical reason to think about why the density difference is small. You get instabilities, it's because there's stratification that would help. No, actually, I don't.
Again,
Is there? Why does it make sense that density is small? Again, the difference. Other than that, is there a?
Yeah, because my understanding is it's sort of the higher the density, the harder it would be for this sort of below to form.
Because stratification.
Yeah, it's like the sort of initial idea of kind of stratification. But yeah, just for like two layers.
It was related to the diffusion, molecular diffusion. It's like you have to very strong difference in density. It's harder for them to mix, but if you have small gradients of density, they are propen to diffusion, something like that.
That will come into play when we start thinking of like the nonlinear part of this. In this scenario, there's no diffusion.
Mentioned that the question of Brent about the small difference between density. In this case, in this case we have two strong difference between densities, but in the example, of course. But the second point of stability is small differences is small. So I imagine that case with a weak difference between densities. So it's physically increase the instabilities.
So in this case, I think, maybe I should have written this a bit differently, but it's relative to the difference in velocity. So if your difference in velocity is higher than your difference in density.
Okay, they are related.
Yeah, it's this equation. Yeah, so it's really the relative to your difference in density. Sorry, I should have maybe rewritten that to be less confusing. But yeah, it's relative to your velocity. Is when, because if you have a very strong density gradient, that's just going to make it harder for shear to kind of drive a perturbation and for that perturbation to grow. Hopefully that makes sense.
Yes.
Yeah, so now if you have a sort of continuous gradient, and we've talked about this a little bit, the frequency at which these kind of natural perturbations of the water column is described by the buoyancy frequency, which was brought up a little bit yesterday. And so in a scenario where you have a negative density gradient, which is kind of shown there, your Beyonce frequency is positive, it's kind of stable. It just indicates that it's in a stable kind of equilibrium. And in the case where you have no density gradient, which is sort of the case when you think of like a classic mixed layer, this is sort of a neutral situation. It's really no buoyancy frequency there. It's no density gradient. And a lot of very smart people have then kind of solved this for a density gradient, kind of this scenario, but now thinking of it in terms of a layered density or a gradient of density versus just two densities. And we're able to find a criteria for, I would say, criteria for instability gradient. And that's when you have a Richardson number, which is the ratio of n squared over s squared, being less than 1/4. And so this is sort of kind of the idea that Grant was bringing up, is that when you have a stratification, it becomes harder for these instabilities to develop. So it sort of dampens the instabilities, while you have a shear, sort of enhances them. And then if you kind of look at the ratio of the two, based on theory, you kind of get a threshold for when that would develop. So again, just to kind of make this clear, this is just an indicator of the potential for shear instability. This is like, if you see this in the ocean, doesn't mean that there is currently mixing happening. This is just an indicator of the potential for instability. As you probably saw, there's a bunch of different sort of solutions that can come out of this equation. But really, it's when you have a solution that's growing, is when you develop an instability. So now you kind of look at like a simulation of a Kelvin-Helmholtz instability, and Caique showed some of this yesterday as well. You can see sort of this situation that we saw in our two-layer model developing, this sort of below roll up. And over time, you'll start to see secondary instabilities develop. And that then starts driving a lot of the mixing that we have. And so you can kind of see overturning, so sort of density gradients that are unstable, which we'll talk about next, that drive mixing. But you also see secondary shear instabilities that can also drive mixing. So the Kelvin-Helmholtz sort of total evolution has potential for mixing. And that's kind of given by that Richardson number criteria. This is some cool experiments to sort of see where this comes up in the ocean. Kelvin-Helmholtz instabilities, there's a couple of other shear instabilities, but this is sort of thought to be the general primary driver of shear-driven mixing in the ocean. So this is a cool experiment where they injected dye to the thermocline and took a lot of cool photographs, but it kind of shows you the evolution of a shear instability over time. And you can kind of see that cool below structure forming and it getting unstable and the kind of density gradients getting mixed up. And Nicole, who will be joining us on the cruise and will be also teaching in the third week, does a lot of experiments like this, just off of the La Jolla Canyon. So feel free to pick her brain about kind of things that she studies. Another way, see Kelvin-Helmholtz instabilities, and this is in a very sort of stratified ocean, is you can see these temperature maps. So this is a scenario where, if you take your mind back to that simulation, you see a density gradient forming. So this is sort of a gradient in temperature that you see here. This is over time, so this is just a few minutes really over time. And you can see this gradient forming and then things collapsing as it mixes and it all becoming one temperature. So this is at different depths, you kind of see this gradient forming and then mixing away. And that's a sign of shear instability as well, something we could look for on the crudes. And in this paper, they also kind of looked at a bunch of these cases. So this is sort of the frequency of how many times they saw this in their time series compared to their epsilon, which we'll talk about later, but it's just a measure of mixing. And you can see that this corresponds to higher mixing as well. So you can see the shear instability develop. You can also see that it's driving mixing. And something I want to also emphasize is that this shear instability is intermittent. And that's probably clear from this image too. You just have a shear instability develop, it mix, and if the ocean gets pretty quiet, it happens again. And you can see that this is an example from the equatorial Pacific, and this is showing you over time stratification and shear across the year. And then with that, they compute Richardson number and kind of see the profile of Richardson number over there too, but they're really looking at this kind of specific depth range here. So in the spring, stratification is pretty strong. So you have a high Richardson number, and corresponding to that is dissipation from chi, which we'll also talk about next, but it's just a measure of mixing. And see that the dissipation or mixing is very low, and then it gets to a point where it's marginally stable, which means that it's just kind of around the 1/4 value. And then in this particular ocean, you have this diurnal cycle of enhanced shear. So every day the shear gets enhanced, and it gets the momentum gets transported into the ocean, and that pushes this kind of marginally stable situation into unstable, and that's what drives mixing. So this is kind of a example of where you can kind of see the ocean sort of in this stable situation being pushed into unstable sort of intermittent. So and it's kind of what happens with mixing in the ocean. It's not always mixing, but it sort of happens during periods kind of intermittently. Yeah.
What is the fill between that for the Richardson number? That's like, is that variability or?
Yeah, I think there's variability. So there's quite a lot happening in the spring, I think. Oh, sorry. Yeah.
And then for the second graph, that S squared divided by 4, what is the divided by 4?
Yeah, so that's a way in which it's represented. Just so if you do that, you can do kind of the n squared over s squared in your brain.
Oh.
And so yeah, where it's these values are similar is where you get kind of a Richardson number that's almost 1/4. That's just sort of a way to show it in to help show that. Any other questions? And sorry, Caique, I will speed run through so you have time. But the sort of debate of whether Richardson number is a good threshold is sort of still a very prevalent one. Mostly because, as you guys probably, as we discussed, it is a sort of linear theory, and it doesn't take into account a lot of the sort of nonlinear processes that we see in the ocean. This is an example of shear and stratification, and the dotted lines here show you dissipation, which is again a measure of mixing. So you can kind of see that the highest dissipation sort of happens where you have Richardson numbers that are lower than 1/4, which kind of shows that this idea generally works, but you do see kind of cases of mixing even at higher Richardson numbers. So that's kind of taking into account processes that are not necessarily shear instabilities or even sort of nonlinear parts of shear instabilities that we don't account for. So this is definitely a sort of question that a lot of people to my understanding and reading, seem to be still exploring. And this is really important because, as you can kind of see, a lot of models use a Richardson number criteria. These are kind of, we'll just focus on the KPP here. And this is showing you measurements of eddy viscosity and thermal diffusivity, again, measures of mixing we'll talk about as a function of Richardson number. And you can see the observations are just sort of these different dotted lines or scattered plot. And then you can kind of see that in the case of KPP, which is a type of mixing scheme, it kind of shuts off or kind of maintains a constant viscosity as the Richardson number increases. Whereas, and it generally follows what the observations show, but there are kind of areas where it doesn't really match. And so it kind of becomes important to think about what a good Richardson number is and how, whether it reflects mixing, because it's used a lot in the way we parameterize mixing. And so another scenario, and if we don't have a velocity gradient, another way in which instabilities can develop and is if you have, when you have the case where the density of the top layer is much higher than the density of the lower layer. And so that's the case here, where because of that unstable density, you kind of create this overturning feature. And that's called a gravitational instability. And similarly, if you were to kind of think of a continuous gradient, you could see that with the buoyancy frequency. So that's if you have a positive gradient, or if you have a negative buoyancy frequency, that's an indication of these gravitational instabilities. And a final kind of speed run, and this is just a teaser, but we'll talk about this a lot in a later lecture. Another way in which the ocean can be unstable is even if it's stably stratified. So that's a scenario where you just have lighter water over denser water. You could also have instabilities develop if you have, because of the fact that heat diffuses a lot faster than salt. So this is just one example of one of those instabilities. So if you have a situation where you have warm and salty water over cold and fresh water, so the warm and salty compensates. And so in the end, the density at the surface is lighter than the density at the bottom. So if you have a perturbation, so something that pushes down this water parcel in this layer of fluid, as it is pushed down, the heat, the warm water and the heat diffuses a lot faster than the salt. And so now it's colder, but still saltier. So it remains denser than the surrounding fluid and continues to sink. And that is an example of salt figures. And that's, it's a very common kind of instability that you see in, especially in sort of polar oceans. And we'll have someone come by who studies that a lot, and will be one of the things we'll discuss, because it's usually an assumption we make that whatever drives turbulence creates the same gradients of temperature and salinity, but that isn't always the case. And so he will talk a little bit about that. And now, Caique will take over and talk about some mesoscale instabilities, which I'm very excited to learn from you.
I have that one question.
Oh, yes, sorry. Yes.
Yesterday we talked about the eddy diffusivity, but right now in a couple of slides of before it was eddy thermal diffusivity. So there is another eddy diffusivities, just thermal or another one?
Yeah. So what Andrea talked about yesterday is eddy diffusivity and momentum. So that is. That's one of the, we'll talk about this in the lectures this afternoon. But one way in which we think about, or we kind of parameterize that, is by looking at variance in momentum, which is what she talked about. So there's a similar equation you can do for temperature, and that is what comes out of that. But if assuming diffusion, yeah, same idea.
Okay.
Down gradients, that kind of thing. Yeah. Cool, you have it set up.
Yeah. All right. So now we're gonna shift to larger scale instabilities that trigger the Kelvin-Helmholtz instabilities. We're gonna talk about these two mesoscale processes. So first, just to give context, some mesoscale motions, they're dynamically characterized by having an order 1 Rossby number and an order 1 Richardson number. This means that at these scales, you have both the planetary vorticity and the relative vorticity being important for your dynamics. Basically, in the Navier-Stokes equations, your advective terms are going to become important. And the Richardson number order 1 means that you're in scenarios where mixing starts to be important. And some mesoscales, they have typical limb scales ranging from
Your video's off. I don't know if you care to be
some
seen,
videos
but
are-
just so you know.
wait. Is it working now?
Yeah. You're on the owl.
Cool. And so they have typical limb scales ranging from hundreds of meters to tens of kilometers. They lie just between the mesoscale and the 3D turbulence. At the mesoscale, your motions are more 2D, and at the 3D turbulence, it's more 3D. So mesoscale is kind of in the edge where vertical velocities start to matter. So some examples of submesoscale phenomena. We have submesoscale eddies, mixed layer eddies that are formed because of baroclinic instability of mixed layer fronts. We have frontogenesis, which is the sharpening of density gradients. And we have non-geostrophic or unbalanced instabilities like symmetric instability. Each of these phenomena, they contribute differently to turbulence. This is a schematic of a kinetic energy cascade. Charlotte is going to talk a lot about it. Here on the left side of the schematic, we have larger scale processes. And on this side of the schematic, we have small scale processes. The energy is injected at larger scales and it cascades down to turbulence through different processes. The submesoscale processes, they lie right between the mesoscale and the 3D turbulence, so they're important to cascade that energy. And one thing about this schematic is that we don't have any internal waves. We're not considering internal waves here, just submesoscale process as that gate wave. And then the mixed layer eddies, they usually contribute to bring energy back to the mesoscale. In the inverse kinetic energy cascade, this is called like the 2D turbulence. You have smaller eddies merging into bigger eddies, and that's the 2D turbulence. But submesoscale frontogenesis and unbalanced instabilities, they contribute to to the forward cascade, bringing energy to the 3D turbulence. Now, frontogenesis, the way that it cascades energy to smaller scales is that you're sharpening your gradients, so you're bringing like you're squeezing your length scale, so you're naturally transferring energy to smaller scales. Here today we're gonna focus more on the unbalanced instabilities because they are the ones that can trigger Kelvin Helmholtz and lead to turbulence. And so some examples of unbalanced instabilities. First one is inertial instability, which is often also called centrifugal instability. We have symmetric instability and gravitational instability or convection that Ankitha just explained to us. Again, the main importance of these instabilities is because all of them, they're going to generate overturning circulations that grow and grow, and they're going to increase shear and lead to Kelvin Helmholtz. Now let's explore a little bit of why do these instabilities form. And first, I'm going to make an analogy. I'm going to give an explanation based on the dispersion relationship. Basically, these instabilities can be seen as the unstable counterpart to internal waves. And then I'm going to talk a little bit about how you can find these instabilities with potential vorticity. Now, from yesterday, we found that the dispersion relation of internal waves is this one on the left. If this number on the right-hand side is positive, we plug this back into the perturbation into the expression for W, and we have oscillations. Now, there's only one case here where you could get a negative value and lead to imaginary omega and have an instability. Does anyone know which scenario is that?
Buoyancy frequency is less than 1.
Exactly, yeah. If your n square is negative and it makes your omega square negative, then you have the gravitational instability that Ankitha told us about. Now, this is the dispersion relationship of internal waves if you don't have a background flow, but Hoskins 1974 derived the dispersion relationship if you have a background flow which has vorticity and buoyancy gradients, and this is that dispersion relationship. And suddenly we have all these different terms, one depending on the vorticity, one depending on the buoyancy gradient in the lateral. M squared is just the absolute horizontal buoyancy gradient. And now in this case, even though that one for positive stratification, your frequency is always real and you have oscillatory solutions, this one can become negative because of this term. If your anticyclone vorticity is too strong, can become negative. Or if this last term here also become really negative, it can generate negative omega. So in those cases, our frequency is going to be imaginary, and we're going to have exponential solutions. Those are going to be the instabilities. So, yeah.
What is capital M?
Capital M is the buoyancy gradient. So, yeah, M squared is the magnitude of the horizontal buoyancy gradient. And so by looking at this from the dispersion relationship, we can really see that sum-scale instabilities are just the unstable counterpart to internal waves. Now, it's not always easy to go out to sea and measure the dispersion relation because sometimes it's hard to get the wave number information of the waves. So what people often do is to use the potential vorticity to find these instabilities. And potential vorticity is a quantity that measures the potential spinniness of a water parcel. It combines the absolute vorticity and the stretching and squeezing of the vortex tube. So for a barotropic flow with homogeneous density, potential vorticity is defined as the absolute vorticity divided by the depth of the water column. And so this property is always conserved in the ocean. So if you end up increasing your depth, if you're stretching your vortex tube, you have to change your vorticity. And there's another expression for the continuously stratified case. And let me just shift here to some lecture notes. So I don't have time to derive all of these with you guys, so I'm just gonna show a couple steps of the derivation. Don't worry about taking notes because it's all on the drive. Sorry, not stepping, but it just has bad contact. All right. So just going over a couple steps of this derivation to show you guys why people use potential vorticity to find stabilities. So potential vorticity on a continuously stratified fluid is defined as the absolute vorticity, the product between absolute vorticity and the buoyancy gradient. You end up with the vertical component of vorticity times the vertical component of the buoyancy gradient. And then you have the meridional component of the vorticity, the meridional component of the buoyancy gradient, and the zonal component of vorticity with the zonal component of the buoyancy gradient. Now, this property Q, it's always conserved. So in the ocean, Q is always constant in the absence of forcing. And if we assume that Q starts with the same sign as the planetary vorticity, in the northern hemisphere, Q is always going to be positive, while in the southern hemisphere, Q is always going to be negative. So to kind of generalize for both hemispheres, you can say that FQ is conserved and it's always positive. Now, there are some scenarios where you can have forcing, you can have cooling at the surface, or you can have friction with topography. And in those scenarios, you can inject or extract potential vorticity. And then in those scenarios, you can lead to negative potential vorticity. And this is when you have the submesoscale instabilities. But why does exactly that happen? For that, we can go back to the Navier-Stokes equations and we look for unstable solutions in the scenario where you have a background flow in thermal wind balance. And so these would be our Navier-Stokes equations again. Shashin showed them to us yesterday. And we're gonna do a separation between the background geostrophic flow and the background ageostrophic flow. Our background flow is gonna be just with a zonal component. So our U velocity is, it has geostrophic velocity and an ageostrophic component. Our meridional velocity is just gonna be the ageostrophic, and our vertical velocity also just ageostrophic. The buoyancy can be divided into the geostrophic component that balances the eugeostrophic and the ageostrophic component. And then another thing just to remember, the thermal wind balance, the one that defines the geostrophic flow on the background, goes like this. You have the vertical derivative of the geostrophic flow equals to the buoyancy gradient in the meridional. And then okay. And then if we plug these definitions back into the Okay, so if we plug these definitions of the background flow and the ageostrophic flow back in our governing equations, they're gonna simplify to these equations here. And most important thing here is that now these governing equations are for the age traffic flow. And on the continuity equation, now we just have the meridional component and the vertical velocity component. And because it's non-divergent in 2D, we can define a stream function. And this will be our stream function definition. We plug this definition back into the governing equation, and everything turns into just one equation, this guy here. This is the Sawyer-Eliason equation. And if we assume that our stream function depends just on a function of yz times an harmonic in time, we plug this back into the equation and we find this PDE here. You can know that the second derivative in time turn into the omega squared, our frequency. And now, last part of the derivation, this equation is a PDE, and it's a second order PDE. I don't know if you guys remember, but a PDE can be parabolic, hyperbolic, or elliptic. For these different sort of PDEs, you're gonna have different solutions. If it's parabolic, we find linear waves. If it's elliptic, we find a balanced flow. And if it's hyperbolic, we have growing and decaying waves, which are the instabilities. Now, the case that we're interested in is the hyperbolic one, but let's do something different and look at the parabolic case and see when this fails. And so for the parabolic case, basically the way to turn the wave for this equation to be parabolic, you combine these three coefficients in a particular way, and then you can see if it's parabolic. In this case, it would be this combination equals 0. And I'm just gonna jump ahead from this equation. You can recombine everything, rearrange everything, and you're gonna find this dispersion relationship. And in this dispersion relationship, you can see that it really looks like the potential vorticity that we saw in the beginning. We have the vertical component of the relative vorticity of the absolute vorticity times the vertical component of the buoyancy gradient, and you have the horizontal component of the buoyancy gradient with the vorticity. And then turns out that your dispersion relationship for these waves is going to be omega squared equal FQ over n squared. And omega is going to be real and it's going to have linear waves only if your FQ is positive. If your FQ is negative, then your omega is imaginary. You're going to have instabilities. So this is the main reason why people use potential vorticity to find the sum scale instabilities. If anyone's also interested in internal waves propagating over like buoyancy gradients and vorticity, this is exactly the way that you find the minimum frequency of internal waves too. So now we can go back to the slides. And so these instabilities, like depending on which part of the dispersion relationship or the PV turns omega negative, we're going to have different names for the instabilities. So in the case where we have this first term turning PV negative, the instability is termed inertial instability. And this is really like the counterpart to inertial waves. For the simple inertial waves, we just have F as the frequency. When it's this component F plus zeta that turns the PV negative. The instability is called inertial instability. And looking at the PV, it's exactly the same component that's going to turn PV negative. And this instability usually happens when you have flow interacting with topography. These are maps from a numerical simulation showing potential vorticity. Blue is when the potential vorticity is negative, so it's where the instability is happening. Usually, this happens because when the current rubs with topography, it increases anticyclonic vorticity so much that you end up with this instability. And again, this instability is going to generate overturning cells that lead to KH, and you can end up with strong turbulence. So on this left-hand side, we have vertical sections around here of the PV. You can see how the instability occurs throughout the water column. And on the right-hand side, we have kinetic energy dissipation rate, which is a measure of turbulence. So we can see where the instability is happening, you have a lot of turbulence happening. Now, the second case is symmetric instability. Symmetric instability happens when the last term is the responsible for turning omega square negative. So the term related to the buoyancy gradient. And yeah, same corresponding term on the PV equation. And this usually happens when you have fronts interacting with winds. So when you have a front and you have a wind flowing on the down front direction, so like on the same direction as the current, you're going to generate an Ackermann flux that tries to put the dense water on this side up on top of the light water on this side. The overturning circulation that you're going to create is the green one. So it's kind of trying to like stratify things even more. Instead of like slumping the front to re-stratify, it's trying to like bring the dense water up on the light water, and that generates instability. And so the way that these instabilities look is that you have these overturning cells along isopycnose, and these overturning cells, they're gonna lead to Kelvin-Helmholtz instability. The first instability that I told you guys about was the inertial waves, the counterpart to internal waves. This one is kind of like the counterpart to inertial waves on sloping isopycnose. Some observations of these, some of the first observations in the ocean were made in the Kuroshio by the Saro. They were crossing the region of confluence between the Kuroshio and the Oyashio. And they had a couple of transects here. They computed the PV, the potential vorticity, and they found this region with strong negative potential vorticity where the instability is happening. And then they also had a couple of floats. And so this is a time series showing stuff distributed in potential density space. Basically, these blobs here, these blue blobs, these regions where they cross strong fronts. And from the floats, they were able to compute kinetic energy dissipation rate. And they saw peaks in the kinetic energy dissipation rate when they crossed these fronts that were with negative PV. Yeah, so this is another example of how submeso-scale instability can lead to turbulence. And then lastly, the last instability is the one because of n squared, the one that Ankitha already talked about. This is the gravitational instability. Here's just a fun video of gravitational instability. Play fast. You have warm water below and cold water below, and you see these plumes forming, generating a lot of turbulence. It's really artistic images. Yeah. So if you guys are interested in like learning more about submeso-scale instabilities and how to classify them, there's this really cool paper by Thomas et al. 2013, where they classify the instabilities with Richardson number angle. And then they find like the different regimes where inertial instability is dominant or symmetric instability is dominant. And yeah, this is a really cool paper for that. And to summarize, some mesoscale motions can lead to either 2D turbulence or 3D turbulence. Mixed layer eddies, the mesoscale eddies, they contribute to a 2D turbulence, merging of eddies into bigger eddies. And then frontogenesis and unbalanced instabilities, they can lead to the forward cascade and turbulence. And these unbalanced instabilities are going to generate KH and mixing, and they can be viewed as the unstable counterpart to intervals. So this was a very quick introduction to some mesoscale stuff. Sorry about all the math, but it's all in the drive if you guys want to take a further look at that. Any questions? Okay. Let's see if there's any fields.
I don't think so.
Okay.
IT stuff.
All right. So everyone's free to go on the break now.